Welcome back, friends, to another session of Strength of Materials. Currently we are dealing EULER's analysis of columns. In previous session I discussed various assumptions which EULER has made in this analysis. So in this session we are going to derive a formula for EULER's critical load, and a little discussion will be there on that formula, right? It will be followed by maybe problems. So here I am drawing a column which is pin jointed on both ends, pin jointed or hinged. So this is hinge A and this is hinge B. Okay, and L is length of the column. L is length of the column, right? And okay, and this column is carrying, okay, this column is carrying critical load of P. So this column is carrying critical load of P. Maybe this is B and this is A. Try to understand, when column carries critical load, the column will be in neutral equilibrium. Critical load is load corresponding to neutral equilibrium. So currently this column is in neutral equilibrium, since it is carrying critical load. Now if I apply a momentary disturbing load, I will apply a momentary disturbing load towards right. When you apply momentary disturbing load, this column will buckle like this. The column will buckle permanently like this. When you apply a momentary disturbing load on column towards right, the column will buckle like this, man, right? I apply a momentary disturbing load, the column will buckle like this, right? Permanently it buckles. Why permanent buckling? It is in neutral equilibrium. If any column is in neutral equilibrium, a small disturbing force make column to buckle permanently. Okay, so now column is buckled like this. For my analysis, I am taking point A as origin. This is my origin, man, right? And I am plotting x-axis parallel to length of the column and y-axis perpendicular to length of the column. I am plotting x-axis parallel to length of the column and y-axis perpendicular to length of the column. You can orient x and y-axis by any angle, man. Always we have to maintain angle between x-axis and y-axis as 90. X-axis need not be horizontal always, y-axis need not be vertical always. You can orient these two axes by any angle according to convenience. So here x-axis is aligned parallel to length of the column, y-axis is aligned perpendicular to length of the column, right? So A is origin, then try to guess what are coordinates of B. Coordinates of B. L comma 0. X coordinate is L because we are measuring x along length, man, right? So x coordinate is L, y coordinate is 0, right? So here I am assuming displacement of the column about center point as delta. So displacement of the column about center of the column is delta, right? Displacement of the column about center point is delta. Now I am taking another plane here, right? Another plane I am taking, maybe this is plane XX. Plane XX. Okay. This plane is located at a distance of x, and the displacement of column about this plane is y. Displacement of column about this plane is taken as y. Okay. So displacement of column at center point is delta. Displacement of column about plane XX is y. And this column is in neutral equilibrium. This column is in neutral equilibrium. This point you have to understand. Now please copy it. Later, we try to derive a formula for critical load of this column. So first copy this column with all these notations. Here I have taken a column which is pin jointed on both ends. This column is carrying critical load. This column is in neutral equilibrium. When you apply a momentary disturbing force, the column buckles like this. Displacement of column at center is delta. Displacement of column about plane x-axis is y. Here x-axis is aligned parallel to length. Y-axis is perpendicular to length of the column. These are the things, man, right? I hope you copied. Right. Here this column is in neutral equilibrium. If this entire column is in neutral equilibrium, every section of column also will be in neutral equilibrium. If your structure is in neutral equilibrium, every section of structure also will be in neutral equilibrium. So here I take equilibrium of bottom portion of the column about plane x-axis. Here plane x-axis is dividing this column into two sections, man. Upper section and bottom section. So for my analysis, I will take equilibrium of bottom span or bottom section of column. Please write it. On taking equilibrium of bottom section of column, bottom section of column about plane x-axis, bottom section of column about plane x-axis, with application of theory of simple bending, with application of theory of simple bending, we get like this, right? EI d square y by dx square equal to minus of bending moment. Theory of simple bending says like this: at the beginning of beams we are going to derive this formula, right? So theory of simple bending says EI d square y by dx square is equal to minus of bending moment. What is bending moment about this point? I should not say bending moment here, I should say buckling moment, but EULER called bending moment, right? So what is bending moment or buckling moment about this point? Just you have to consider only bottom section. In bottom section only one force is acting, that force is P. So P into Y. So this is equal to minus P into Y. EI d square y by dx square is equal to minus term, that is equal to minus P into Y. Then I bring this minus Py to left side. So this equation becomes EI d square y by dx square is equal to plus Py is equal to 0. On bringing minus Py to left, it becomes plus Py. Then I divide this entire expression with EI. On dividing with EI, the above expression becomes d square y by dx square plus P by EI into Y equal to 0. On dividing above expression with EI, we are getting this one. D square Y by dx square plus P by EI into Y. Here, let P by EI is equal to K square. I am assuming like this man, right? P by EI is equal to K square. You know, here K is not radius of gyration, man. K is a constant. Always we can replace a group of constants with another constant. See here, for the given beam, for the given column, E is constant. For the given column, I is constant. And this P is also constant. Why P is constant? Here P is critical load. Critical load of column is constant. It is not variable. It is a special load, man. That is a particular load, particular specific load. So P is constant, E is constant, I is constant. This group of constants I am replacing with another constant. That constant is K square. Now the above expression becomes D square Y by dx square plus K square into Y is equal to 0. On replacing P by EI with K square, this equation becomes D square Y by dx square plus K square Y is equal to 0, right? So what is this, man? It is second order simple differential equation, right? It is second order differential equation, a linear differential equation, simple differential equation. The general solution of this differential equation could be written as Y is equal to C1 cos kx plus C2 sin kx. In many subjects, in many topics, you may encounter this differential equation. You know, since we are dealing linear systems, or since we are assuming systems are linear, in many subjects, in many topics, we may get this differential equation. Wherever you get this differential equation, the solution could be written in this form. Y is equal to C1 cos kx plus C2 sin kx, right? Here we have to find this constant C1 and C2 by using boundary conditions. What boundary conditions I can use? Don't copy, man. I'll give time, then you can copy, right? Just listen here. What boundary conditions we can use? Here Y is displacement, right? At x is equal to 0, Y also is equal to 0. X is equal to 0 means point A or pin joint A. About pin joint, slope is possible, not deflection or displacement. About A, displacement will be 0. That means Y is 0. If you put this boundary condition in above expression, so 0 is equal to C1 cos k into 0 plus C2 into sin k into 0. C1 cos k into 0 plus C2 sin k into 0. First let us deal this, man. K into 0 is 0, sin 0 is 0, 0 into C2 is 0. So second term is becoming 0. Then come to first term. K into 0, 0, cos 0 is 1. 1 into C1, C1, C1 is equal to 0. This is already 0, only here we are getting C1, C1 is equal to 0. So by using first boundary condition we got C1 is equal to 0. Now come back to this equation. Here C1 is 0, man. So the above solution is reduced to simply Y is equal to C2 sin kx. Why? Because C1 is already 0, right? So Y is equal to C2 sin kx. So here we have to find C2 by using second boundary condition. What is second boundary condition? At x is equal to L, Y is 0. X is equal to L means second pin joint or pin joint B. At pin joint there is no possibility of deflection or displacement. Only slope is possible. Here Y indicates deflection or displacement of column. Okay. Alright. Let us use second boundary condition. Let x is equal to L, y is equal to 0. Let x is equal to L, y is equal to 0. This boundary condition is given by pin joint B. Then 0 is equal to, I am putting this boundary condition in this expression, man. Don't worry about this now. In this expression already C1 is 0. This expression is reduced to C2 sin kx. So 0 is equal to C2 into sin KL. 0 is equal to C2 into sin KL. So you may copy up to this point, man. From this point onwards, I will discuss later, right? So copy all these contents and come up to this point. Then I will explain. You might have copied. Let us proceed, man, right? So from this point onwards, I will discuss. Alright. So 0 is equal to C2 into sin KL. Here C2 could be 0 or sin KL could be 0. If C2 is 0, the entire expression will be 0. If sin KL is 0, there also you will get 0, man. So C2 could be 0, sin KL also could be 0. So what is your understanding, man? C1 is already 0. C1 is already 0. If C2 is also 0, there will not be any solution. If C1 is 0, C2 is 0, for any value of x, y will be 0. Understand? You see here, man, for any value of x, y is 0. Only here no deflection. Only here no deflection. All other points are carrying deflection or displacement. So C2 cannot be 0. If C2 is 0, you will not get any solution. So that is why sin KL should be 0. C2 cannot be 0. Right? So sin KL is equal to 0. Sin KL is equal to 0. When sin value becomes 0? When sin theta becomes 0? When theta is equal to n pi. Here what is theta? KL. When KL is equal to n pi, sin value becomes 0. N is any integer value, either 0 or 1 or 2 or 3. N is any integer value. Okay, for any integer value of n, sin theta becomes 0. Bring L to other side. So k is equal to n pi by L. K is equal to n pi by L. Square both sides. So n square pi square by L square. K square is equal to n square pi square by L square. But what is k square? But k square is equal to P by EA. We assume k square is equal to P by EA. So P by EI is equal to n square pi square by L square. Keep P on one side, bring EI to other side. Then it becomes P is equal to n square pi square EI by L square. Okay? P is equal to n square pi square EI by L square. What is this P? Critical load. Okay? So please copy these little steps. Take some half minute and copy. I think you would have written these contents. Write what is P. Write what is P. P is equal to buckling load or critical load or Euler's load or crippling load or bifurcation load, etc. Please copy all these words, man. In GATE exam, they may use any of these words. So P is buckling load or critical load or Euler's load or crippling load or bifurcation load. Please copy all these things. So P is equal to buckling load or critical load or Euler's load or crippling load or bifurcation load. You may put a small gap here. Bifurcation load. Bifurcation load. So we derived a formula. When a column is pin jointed on both ends like this, the critical load of column is given by n square pi square EI by L square. N square pi square EI by L square. So this is one of the important formulae in SYM. Many GATE questions came on this formula. So this is very, very important formula. Many GATE questions, man. They are coming regularly. Again in coming GATE exams, they may give another question on this formula, right? Let us try to examine this formula, man, right? Let us try to examine this formula. First, you know, Euler's critical load is proportional to E into I. What is this E into I? In beams, E into I is called flexural rigidity. Flexural rigidity. E into I is called flexural rigidity. So I should say here, I am writing I2, man. What is I2? Lowest moment of inertia of the column's cross section or minor principal moment of inertia. You know, when you apply critical load of column, about which plane it will fail, or about which axis it will fail. I should not say fail, right? About which axis it may buckle. Always it will buckle about z-axis or y-axis? No. It may buckle about an axis which carries lowest moment of inertia, man. Column always buckles about axis which carries lowest moment of inertia. That is why here I2. Okay? So Euler's critical load is proportional to flexural rigidity. E into I is called flexural rigidity. Okay? Write down first point. Euler's critical load is proportional to Euler's critical load is proportional to Euler's critical load is proportional to flexural rigidity E into I. Flexural rigidity, flexural rigidity, flexural rigidity, right? It is proportional to flexural rigidity. If flexural rigidity of column is more, Euler's critical load also more. What is critical load? Critical load indicates load bearing capacity of column without buckling, or safe load. Critical load indicates safe load. More the flexural rigidity, more the load bearing capacity of column without buckling. Without buckling. Okay, second point. This formula is saying P is proportional to E. Is it not, man? P is proportional to E. Write down second point. P is proportional to E. What E indicates? In beginning sessions of SOM, I told Young's modulus always indicates stiffness, not strength. So Euler's critical load is proportional to stiffness. Why? Because E is function of stiffness, or E indicates stiffness. So here one important point, man. Euler's critical load is derived on the basis of dash. Euler's critical load is derived on the basis of dash. Strength, stiffness, hardness, all of the above. What is your answer, man? Only stiffness. Only stiffness. Previous gate question. Euler's critical load is defined or derived on the basis of stiffness of column's material or stiffness of column, not anything else. It is not function of strength. It is not function of strength. You know, a question came, man, right? A question came in GATE exam. Already I discussed this question at the beginning of SOM, right? So they are given two columns, column 1, column 2. Length of both the columns is same. Young's modulus is also same. Both are carrying same moment of inertia. Length is same, E is same, I is same. What is difference? Strength of first column is double of strength of second column. Strength of first column is double of strength of second column. Like this they are given data. Then question, critical load of first column is how many times of critical load of second column? They asked, critical load of first column is how many times of critical load of second column? How many times, man? This formula is saying critical load is function of E, I and L only. Critical load is not function of strength. Strength of first column may be double, triple, 5 times, 10 times, 100 times, man. Critical load doesn't change. Critical load doesn't change. What is the answer, man? Answer is same. Critical load of both the columns is same. Another question came. Two columns they have taken. Two columns they have taken. Or only one column, for example. Okay, length of this column is L, Young's modulus is E, moment of inertia is I, like that, man. What is critical load of this column? N square pi square EI by L square. Now, I double length And I double strength also, man. That means I have to take different materials, obviously, right? Without changing stiffness. So I double length, I double strength also. Critical load becomes dash. Critical load becomes dash. What will happen to critical load, man? Critical load is not function of strength. You may double strength, man. It doesn't worry. It doesn't make any difference to critical load. So strength is double, length is double. What will happen to critical load? P is independent of strength, but P is very much function of length. When length is double, the denominator becomes 4L square. That means critical load becomes 1/4 of original load. 1/4 of original critical load. Like this, questions are coming, man. Regularly questions are coming. Similarly, if you observe this formula, Euler's critical load is inversely proportional to L square. Euler's critical load is inversely proportional to L square. If you increase length, P will decrease. If you decrease length, P will increase because they are inversely proportional to each other. A standard question, very popular question. If length of column is double, what will happen to critical load? If length of column is double, what will happen to critical load? If L is double, what will happen to critical load? Critical load becomes 1/4 of original critical load. 1/4 of original critical load. Another option, if length is decreased to half, what will happen to critical load? What will happen to critical load? I will decrease length to half. If L becomes L by 2, what will happen, man? Critical load will become 4 times. Like that, man. If L is decreased to L by 3, what happens? Critical load becomes 9 times. If L is decreased to L by 4, critical load becomes 16 times. Like that, man. So critical load is inversely proportional to L square. It is inversely proportional to L square. If I increase L by 20%, what will happen? If I decrease L by 20%, what will happen? So this kind of problems I am going to do after completion of concept. We are going to do some numericals. In those numericals, I try to do this kind of things, man. So for the time being, write few points here. First one. If length is increased to double, Euler's critical load becomes dash. Euler's critical load becomes dash. Euler's critical load becomes dash. What is your answer, man? L is doubled, man. L has become 2L. In place of L, put 2L. 2L whole square. So what will happen to critical load? When L is becoming 2L, critical load will be like this. P is equal to N square pi square EI by 2L whole square. That means N square pi square EI by 4L square. Original critical load is this. N square pi square EI by L square. Now critical load is this. N square pi square EI by 4L square. If you compare this and this, what is your understanding? Critical load is decreased by 4 times. Our critical load becomes 1/4 of original critical load. So write down answer. 1/4 of critical load. The answer is 1/4 of critical load. 1/4 of critical load. 1/4 of critical load. If you want further, further explanation, you may write like this. Original critical load is equal to this much. Original critical load is equal to this much. When length is L, this is critical load. When length is 2L, this is critical load. This is original critical load. This is critical load of column when length is double. So on comparing these two, you'll understand critical load is 1/4 of original critical load. 1/4 of original critical load. Okay? Let us do one more point, man. Simple thing. If length is decreased to half, if length of column is decreased to half, write down, man. If length is decreased to half, if length of column is decreased to half, If length of column is decreased to half, critical load becomes dash. Critical load becomes dash. So original critical load equal to n square pi square EI by L square. Now final critical load equal to n square pi square EI by L by 2 square. You know, length is decreased to half. That means L by 2. If we simplify this, you get 4 n square pi square EI by L square. This much you get. If you compare these two loads, this is original critical load. N square pi square EI by L square is original critical load. This is critical load of column when length is decreased to half. So if you compare these two, what is your understanding, man? This critical load is 4 times of original critical load. So the answer is, the critical load becomes 4 times of original critical load. 4 times of original critical. First write down answer, man. 4 times of critical load, then you may copy this, right? 4 times of critical load, then you may copy this original critical load, n square pi square A by L square, final critical load, 4 into n square pi square A by L square, and comparing these two, the critical load of column is 4 times of original critical load when length is decreased to half, right? So please copy these two terms. So a few more problems we are going to do as part of classroom workbook, right? So this is your understanding. I hope you copied. Now, some of you might be puzzling. What is this n? I wrote n square like that, man, right? What is this n? What is meaning of this n? What is effect of n on critical load of column? Okay? Write down, man. N is equal to mode number. N is equal to mode number or mode shape number. N is equal to mode number or mode shape number. So please copy. N is equal to mode number or mode shape number. Mode shape number. Okay? Right. If any column buckles like this, mode number of the column will be 1. If any column buckles like this, mode number is 2. If any column buckles like this, mode number is 3. If any column buckle like this, mode number is 4, and so on. Please copy all this. If any column buckles like this, mode number is 1. You know, don't write all these things, man, right? Simply you may copy like this, man, right? If any column buckle like this, mode number is 1. So first you may copy this, then copy this, and so on. So let us add these things, you know, this is L by 2, this is L by 2, this is L by 3, this is L by 3, this is again L by 3, This is L by 4, L by 4, L by 4, L by 4. Here L is length of column. This is L. This is L. Please copy, man. If any column buckles like this, mode number will be 2. This is mode number 3 or mode shape number 3. Mode number 4 or mode shape number 4. If any column buckles like that, that is same as this man, right? Both are same. So if any column buckles like that, mode number is 1 or mode shape number is 1. Mode shape number is 1. I hope you copied. We clearly know P is proportional to n square. Euler's critical load is proportional to n square. If you increase n, critical load will multiply. I should not say incrementation, right? It will multiply. Now, for example, if n is double, critical load becomes 4 times. If n is triple, critical load is 9 times. If n is quadruple, critical load becomes 16 times. So, by increasing mode number, the critical load is getting multiplied. It is multiplying. Indirectly, critical load of this column is pi square A by L square only. What is critical load of this column, man? 4 pi square A by L square, because n is equal to n square is 4. What is critical load of this column? 9 pi square A by L square. What is critical load of this column? 16 pi square A by L square. What is next? 25. Next, 36. Next, 49. Next, 64, 81, 100. When you increase mode number, critical load is getting multiplied, man. 4 times, 9 times, 16 times, 25 times, like that. So we have to increase mode number. Little explanation here. If any column is buckled like this, instead of like this, if any column buckles like this, instead of like this, critical load becomes 4 times. 4 times of original critical load. If any column buckles like this, critical load becomes 9 times of original critical load. If any column buckles like this, critical load becomes 16 times of original critical load. Critical load is getting multiplied when you increase mode number. What is next, man? N is equal to 5 will come 25 times. Next 36 times. Next 49 times. 64 times. By increasing mode number, critical load is getting multiplied. So theoretically, mode number could be infinity also. Theoretically, mode number could be infinity also. When mode number is infinity, critical load also will become infinity. Okay? Now a question, man. This entire stuff is purely theoretical, or practically we can increase mode number. Can we increase mode number practically, or it is only theoretical discussion? It is n is equal to 3, n is equal to 4, n is equal to 5. When you increase mode number, critical load will increase. All this discussion is, theoretical, or is it practical? Can we increase mode number practically? That is my question. Is it theoretical or practical? Many students may think it is theoretical. Many students may think it is theoretical. I am saying it is very much practical. It is very much practical, man. Right? We are using this. For instance, I put one stop at center of the column, man, right? I put one stop at center of the column. I don't allow any deformation at center of the column. Stop means it doesn't allow any deflection of column. So when you apply load, column try to buckle like this. But at center I am putting stops. So the column cannot buckle like this. When column is unable to buckle in first mode, it will try second mode like this. When you put a stop at center, column buckles like this. When I put another stop, man, right? I put a stop at L by 3. Another stop at L by 3, right? Two stops I may put here. I don't allow any deflection here, any deflection here. The first column try to buckle like this. Since you are restricting deflection at L by 3, it cannot buckle like this. Then it will try second mode. At L by 3, you are not allowing any deflection. So it is also not possible. When second mode is not possible, it will buckle in third mode. Similarly, by putting another stop here, I may expect fourth mode. By putting another stop, I may expect fifth mode. So by putting stops at appropriate points, we can increase mode number. It is very much practical. It is very much practical. Don't think it is theoretical. For instance, a 5-story building is there. A 5-story building is there. Currently, I am in third floor. I am in third floor. There is one column there. I am watching a column there. I am in third floor. A column is there like this, man. Maybe here, right? A column is there. Now listen carefully. With respect to this column, what is this entire floor? When column tries to buckle, this entire floor will restrict or assist. Understand? When column tries to buckle, the total floor will try to resist buckling of the column. Total floor will try to resist buckling of that column. So that means what? With respect to column, every floor is a partial stop. With respect to column, every floor behaves as if it is a partial stop. So 5-story building means how many stops will be there? 5 stops will be there. In 40-floor building, how many stops will be there? 40 stops will be there. Right? In 70-floor building, how many stops will be there? 70 stops will be there. So with respect to column, every floor may behave as if it is a partial stop. And second point, usually in construction of buildings, first you construct columns, then you join all columns by horizontal members. These horizontal members are beams. All columns are connected by beams. With respect to column, what is beam? What is beam? A stop. When column tries to buckle, beam will try to resist. Of course, I should not say full stop. It is a partial stop. It is a partial stop. So with respect to every column, a beam is partial stop. You know what is longest building or highest building? Burj Khalifa. How many floors? So many floors, man. So many floors. That means how many partial stops with respect to individual column. I should not say total building. With respect to an individual column, how many partial stops would present? So many partial stops. Then what would be the critical load of that column? It's very, very big. As you are increasing number of stops, mode number will increase. As mode number increases, critical load also will increase. Okay? So unknowingly or knowingly, we are using concept of stops, concept of increasing mode numbers. Increasing mode numbers. One building I want to describe, American military building. Before Pentagon, there was one building, American military building. That building was totally constructed by aluminum columns and aluminum beams. Metal columns, man, metal beams. At the top, they laid some asbestos sheets. It is not concrete building, very old building, before Pentagon. In Civil War time, they have constructed that building. If you observe every aluminum column is very long like this. Aluminum column is very long, but diameter is very small. Diameter of this aluminum column is very small, it is long, and load on this column is enormous. Load on every column of this building is very big, but columns are not buckling. Columns are not buckling. Instead of bearing large load, columns are not buckling. What is the reason? At every 3 meters, they put one stop like this. Every 3 meters, a stop is placed. With every stop, mode number will increase. With incrementation of mode number, critical load will increase. So, we are using this concept, man. We are using this concept. Always column need not buckle like this. You can make this column to buckle in second mode or third mode or fourth mode or fifth mode or sixth mode or seventh mode. So, higher modes are possible. Very much possible. We are using it, man. We are using it. We may not aware, but we are using it. Okay, so here I want to introduce a parameter here. Let M is equal to number of stops. Please copy, man, don't wait. M is equal to number of stops. N is equal to mode number. N is equal to mode number. So this is second mode, man, right? N is equal to, I put one stop here. I put one stop here. And this is third mode. I put two stops. I put two stops. Here N is equal to 3. So tell me, man, what is relation between number of stops and mode number? I can easily say mode number N is equal to M plus 1. Here no stop, M is equal to 0, N is equal to 1. Here number of stops is 1, M is equal to 1, mode number is 2. Here number of stops is 2, M is equal to, N is equal to 3. I can easily say N is equal to M plus 1. Then Euler's critical load of this column becomes M plus 1 whole square pi square A by L square. M plus 1 whole square pi square A by L square. Either N square pi square A by L square or M plus 1 whole square pi square A by L square. Okay? So please copy these contents. In coming session, I continue the remaining part of derivation and remaining end conditions. Even in coming session, we are going to deal effective length of column. So these things we are going to discuss. Okay, so until next session, I should say goodbye. Have a nice day. Let us meet again in coming session. Thank you very much for listening me. Thank you.